Hello everyone and welcome to problem set number 5 examples. First of all, we have this trig function and where is it increasing? So increasing means the derivative is positive. So I will need to take the derivative, set it equal to 0 and solve for x. First, I'm going to take a look at the function and get an idea of how many solutions I need to be looking for. So here's the original function. And then the window should go from 0 to 2 pi. And the y values, -5 to 5 should be good enough to see the graph. So this part is decreasing. And then this part would be increasing. And then decreasing. And then increasing. So there's one interval right here where it's increasing. And there's one interval over here where it's increasing. Now to find out, where does the derivative equal 0? So the derivative of cosine will be negative sine, so -2 sine of x. And the derivative here will also be negative sine of 2x. And then the chain rule tells me you also need to take the derivative of 2x and multiply by that 2. And I notice that this has a -2 and this also has a -2, so set it equal to 0 and I'm going to factor out the -2. So this will leave behind sine of x and I'm factoring out this negative, so it's going to leave plus sine of 2x. So when I set this equal to 0, there's two main principles in solving trig equations. One is the trig functions should be the same, and they are. That's good news. The other is that the argument should be the same. So it should say x and x or 2x and 2x. So for that, I'm going to look over to this little box of trig identities that happens to be sitting right here. And a trig identity for sine of 2x is that it's 2 times sine of x times cosine of x. So you can take something that has a double angle and then it just has a single x over here. If you happen to have cosine of 2x, then you can use the trig identity that it equals cosine squared of x minus sine squared of x. And then it no longer has the double angle, it just has a single angle. Sometimes when you use this one, you also do need to use sine squared plus cosine squared equals 1. That way, if you need to only have sine in it and it has a cosine squared, well, you could solve for cosine squared. It would equal 1 minus sine squared, and then just plug that in right there. Okay, but for this one, I just need this one. But these three are very helpful quite often. So when I set this one equal to 0, because of course -2 will never equal 0, so that's not going to give us a solution, then I would have sine of x plus, and now replace the sine of 2x with 2 sine of x times cosine of x. And that way, all of the arguments just have x. And then you might say, yeah, but now you have this cosine. Well, it's not a problem because I can factor out a sine. So when you factor out a sine x, it leaves behind 1 from this part and then 2 cosine x. And now that it's been factored, you can separate these and say one possibility is that sine of x equals 0. Another possibility is that 1 plus 2 cosine of x equals 0. And for this one, you could just look at the sine graph and it equals 0 at 0 and at pi and at 2 pi. With this one, I would move the 1 to the other side so that it becomes -1 and then divide by this 2. So this one is really saying, when does cosine equal a -1/2? So the cosine graph looks like this. It starts at 1, it goes down to -1, and then goes back up, and here's 2 pi. This one is saying, when does it equal a -1/2? So if you put that on the y-axis and go straight across, there's going to be 2 places where cosine equals a -1/2. And I could use cosine inverse to find the first solution. So if I put second cosine inverse of a -1/2, then that looks like it's some type of like pi over 3 or 2 pi over 3. What is it? So if you divide that by pi and ask the calculator what fraction that is, that's 2/3. So this one is at 2/3 of pi, or 2 pi over 3. And then this one is to the left of 2 pi, so this would be at 2 pi minus 2 pi over 3. Now this is 6 pi over 3 minus 2 pi over 3, so that equals 4 pi over 3. Okay, so now I'm going to take all of my answers and put them in order. So first would be 0. Next would be 2 pi over 3. Next would be pi. And then 4 pi over 3. And then 2 pi. And I was asking, where is it increasing? So if you go back to the graph and look at these, let's see where it's increasing. So go back to the graph, and from 0 to 2 pi over 3, that should be decreasing. So this point right here should be 2 pi over 3. Trace and see, is that 2 pi divided by 3. So that's good. So this part is decreasing, and then it's going to be increasing. So that should be, I can even start writing down my answer, increasing from 2 pi over 3, and then the next one should be pi. So if you put pi, okay, so that little middle part right there is increasing to pi. And then this should be the 4 pi over 3, because that's the next solution. So 4 pi divided by 3. And then from there until 2 pi, it's increasing. So together with 4 pi over 3 to 2 pi, those are the places where it's increasing. Okay, then on to number 2. What about, I didn't finish the sentence. Where is this function? Concave up. So concave means second derivative. Concave up means second derivative is positive. So I'll save the graphing until after I do the work. So take the derivative. So the first derivative would be 4x cubed plus, this one will be 12x squared minus 420 x plus 4. Then go on to the second derivative. So this will be 12x squared plus 24x minus 420. And then set that equal to 0. And I could do the quadratic formula with these numbers the way that it is, but I noticed that all of these can be divided by 12. At least I'm pretty sure 420 can. 420 divided by 12. Yeah, that works. That's a 35. So what I could do is I could factor out a 12, and it would leave x squared plus 2x. And then if you factor a 12 out of the 420, that's a 35. So then minus 35. And usually I would just do the quadratic formula, but if I use a 7 and a 5, I think this one could be factored. If it can't be factored, you could always do the quadratic formula. Quadratic formula always works. Factoring works sometimes. Let me see. If I use a 7 and a 5, and if I make this one positive and this one negative, Does it actually work? So the middle term, this would be 7x positive. This would be 5x negative, so that leaves behind 2x. A negative times positive, hey, it actually works. All right, so there's two solutions. When you set this one equal to 0, you'll get x equals 5. And when you set this one equal to 0, you get x equals a negative 7. All right, there's the two important points. That's where the second derivative equals 0. Now let's see what's going on with the graph so you can see where's it concave up. So this one is x is raised to the 4th plus 4x is cubed minus 210x is squared plus 4x. And the important numbers are a 5 and a negative 7. So if I go to zoom standard, let's see if we could see it. And I cannot see much of it. So what I do is I then say, okay, one important number I got was 5. So where's that? Oh, that's way down there at negative 4,000. Another important number was a negative 7. Where's that? Oh, way down there at almost negative, it's in the 9,000s. So it seems that the y values are really way down there. So I'm going to go to negative 10,000 and then see if I could see the graph. All right, so I got x equals negative 7, trace, and put a negative 7. And then I also got a 5. All right, now keep in mind this is not the first derivative, because if we did the first derivative, we would have gotten this as a minimum and this as a maximum, but we're talking about the second derivative. Second derivative is telling us where's it concave up and concave down. So from negative 7 until 5, that seems to be, this is concave down. And then this part would be concave up. Now, another thing you could do if you don't trust the graph is you can make a number line and say one important number I got was negative 7. The other one I got is 5. And the second derivative equals 0 here and here. And then you could say this is about the second derivative. And then you could pick a test number over here, like negative 8, and then plug that into the second derivative and see if it's positive or negative. So if I take a negative 8 and plug it into the second derivative, that would be 12, and then negative 8 gets squared, plus 24 times a negative 8 minus 420. That equals a positive number. So that means that for this whole interval, that would be positive, which means it's concave up. And then pick a number in here between these two. Probably the easiest would be 0. And if you plug a 0 into the second derivative, this would be 0, this would be 0, this would be negative 420, which means that it's negative in between those two, or concave down. And then pick a number over here like 6 and plug that into the second derivative. So 12 and then 6 gets squared plus 24 times 6 minus 420. And that, strange coincidence, 156, 156, but that's a positive number. So the 156 itself isn't important, it's just that this is positive. So this is concave up. And the directions I asked for, where's it concave up? So that's this interval and this interval. So for concave up, it's from negative infinity until you get to that important point, negative 7. And then also this right side over here, so that's from 5 to infinity. Next up, what about the mean value theorem? So for the mean value theorem, you first of all substitute these numbers into the function, find out the y values. So f of 10 equals 10 squared plus 8 times 10 plus 5. How much is that? 185. Now substitute the 1 into the function. So 1 squared plus 8 plus 5. So this would be 9 plus 5, that's 14. Right? 8, 9 with 5 is 14. And then you find the slope. So subtract the two y values, 185 minus 14 over, and then subtract the two x values. So I went this one minus this one, so I have to go 10 minus 1 to be consistent. And then see what that equals. So this is slope of the secant line. So if you take 185 minus 14 and divide by, that's a 9, happens to equal a 19. Then what the mean value theorem says is, if you take the derivative, there has to be a place where the derivative equals this number. So it's basically saying this is the slope of the secant line. If you take the derivative, that's slope of the tangent line. There has to be a place where the two are equal. So the derivative would be 2x plus 8. So there has to be a place where 2x plus 8 equals a 19. And then you could just subtract 8 from both sides. So 19 minus 8, that's going to be an 11. And then x is 11 over 2. And then one small technicality is that the mean value theorem calls it the letter C. So C equals 11 over 2. And then we start doing some antiderivatives. And basically at this point, there's only two ways for us to find antiderivatives. By the time we finish the semester, we'll have more ways. And when you take Math 3B, there's even more ways. One is basically if you find the antiderivative of x to the n, then you add 1 to the exponent, and then you divide by that n plus 1, and then at the end you put a plus c. And that's how we're going to do this one. Although first, I do need to do algebra and multiply this out before finding the antiderivative. So the integral of x cubed plus 7x squared. And these two things, the integral symbol and the dx, they go together to say find the antiderivative of this. And part of what this is doing is telling you that x is the variable. So now just use this. So add 1 to the exponent, that becomes x to the 4, then divide by that number. And we're done with the first one. Next, the 7 can just sit there, and you add 1 to the exponent, which becomes x to the 3, and then you divide by 3. And then at the end, put a plus c, and that one's done. Now, the other way that we can find antiderivatives at this point of the semester is basically you know derivatives so well, you could just look at it and see what the answer is. And that's how these two are. Another thing you can do with antiderivatives is if there's a constant that's being multiplied, like this is really 7 times 1, then you can factor out that 7. And then it leaves 1 over 1 plus x squared. And then your brain goes, oh, I recognize that. That comes from the derivative of tangent inverse. And I say, you are so right. That means the antiderivative of 1 over 1 plus x squared is the tangent inverse. Put a plus c at the end, and it's done. And then this one is almost the same, except I didn't put the square on it. So you can factor out this 7 like last time. And then if you look at this one, this is very much like the natural log, because if you have y equals the natural log of x, its derivative equals 1 over x. That means if you're going backwards, which is what the antiderivative does, the integral of 1 over x equals the natural log of x plus c. And then that's how this one is done, except that's not just an x, it's a 1 plus x, so that should be a 1 plus x. So the 7 stays there, and then it's going to be the natural log of 1 plus x, and then put a plus c.